Start with cuboids. For example, we have cuboid, something like this. Okay, so uh,
Like,
when we have to find out the first of all total surface area of a cuboid, say
is it like 2LW
exactly,
plus 2BH,
yeah, it is.
like all that?
But how do we find it? See, in a cuboid, all the faces that are there, you are aware with what are faces, what are vertices, what are edges, sides, right?
Yeah.
So this is what we call as a side or an
Edge.
this is what we call as a vertex. These are vertices and these are faces. All these rectangular figures that you can see. So total surface area in any kind of figure is the sum of every area that we can see from our naked eye if we are looking from all the directions present out there. Okay, so if we look at the cuboid in the same way, we will see six rectangles being placed perpendicular to each other. Right. The first one is ABCD, then DEFG, then FGBC. Right. Three here now, three something like this. Okay. So these are the six faces that we can see. And for every face, so for example, this face is exactly congruent with this face. And the area for this face is what? This is a rectangle with dimensions L and H. So L into
Yeah.
H is the area of ABCD and the same goes for EFGH as well. So 2 times LH. Similarly, if we are saying it for this figure, this is congruent with the top half and the area is L into B. So 2LB. 2LB plus 2LH. And if we are doing it for these two congruent figures, the area of them are equal to BH. So 2BH also. Therefore, the total surface area will be equal to 2 if we are taking out to be common LB plus BH plus HL. Okay, any doubts?
Okay. Yeah, I got it.
Okay. Now, if we are talking about the lateral surface area or LSA of the cuboid, then for every lateral surface area or the curved surface area, what you have to think that you are just there is a room of the like the figure you have to think it of as a room in which you have been kept. Okay, so you are standing on the floor obviously. So the floors area and the roofs areas, the top and bottom areas that you have to basically skip. Okay, when you are finding out the lateral surface area or curved surface area for any kind of figure. So similarly, like this cuboid, what is a cuboid? Cuboid is the like actual shape of the rooms that we live in, right? So this is a
Mhm.
room in which the bottom area and the top area you are ignoring. So it means 2 LB area you are ignoring. LB from the top, the bottom, and LB from the top. So this LB would be eliminated simply 2 times BH plus HL would be the area. And also from these two terms, we can take H to be the common term out. 2HL plus B. This will be the lateral surface area of a cube. Okay, any doubts?
Oh, no.
Okay.
Mhm.
Now, if we are talking about the volume of a cuboid, now it is equal to L into B into H. But why it is equal to L into B into H? Say for example, we have an area of the bottom L into B. The same area we are integrating it over again and again infinite times until this
Yeah.
small thin layer of area has completed this H height. So that is how area is being found. Area is first of all found for a second surface, sorry, not second surface, 2D surface, and whatever the area of that 2D surface is, and like the height for which we are integrating it over, like this 2D area for this surface L into B, we are integrating this over for a height H, like this infinite times until it has reached this EFCD point. So this whole thing where the area in times of height through which we have integrated it, that is simply what we call as the volume of the figure. Okay,
Okay.
it is going to be equal to LBH. Any doubts?
For the lateral surface area, so it's
Mm-hmm.
only the top and bottom that's gone. So why can't we just
Yeah.
say that like the
Yeah.
other
Why can
one?
we just say that it is equal to 2L into B plus H?
Yeah.
Yeah. Because the thing is that when we are drawing a cuboid, the length is always assumed like this, L. Or let me rephrase my statement. Even if you are not assuming this to be your length, but for this figure, we have assumed this is L, this is B, and this is H. Am I right? Like the general uh, assumption is this only, that the bottom part is what we consider as the base rectangle with dimensions L and B,
Yeah, I
the
get it.
2D figure,
So
right?
what we can replace L with H and that'll become the height,
Yeah,
right?
yeah. We can actually replace L with H, but L this side, now this is all in almost all the cases it is gonna be the length only, because the base rectangles are considered to be either this rectangle, or the most general convention is assuming it to be this rectangle. So according to the most general convention, this formula is correct and this figure is correct. Okay. If you have been like given a question anywhere and the convention has not been given, then what convention are you going to use? The one which I have drawn here. Okay, this is length, this is breadth, and this is height. Again,
Okay.
you can also assume this to be the length, which we have assumed. This is always gonna be like length. Okay, you can assume this to be the breadth and this to be the height. Like this is again not the most common assumption. The most general assumption is this much only, which I have drawn, that this is the base rectangle and this is the height through which we have integrated it. Okay,
Yeah.
so according to this most common assumption, this is the LSA formula that we have got. If you have changed the assumption, obviously the formula is going to change. That is why I have not just written all these three formulas. I have like made you understand how do we derive it and why it is like this only. So basically, you know the concept. We have to ignore the top and bottom of the figure of the room that we are in, and that room is the that of the shape of the figure that we are discussing. So
Okay.
the top and bottom area has to be ignored. Therefore, LSA has came out to be this. Now, if the assumption change or a question, say for example, then you know what to do. Okay, so you will
Yeah.
derive it. Any doubts?
No.
Okay. Okay. So since we have done this thing, now I'm not going to write everything for a cube, because that will just be a repetition of the whole thing. Because in a cube, L is equal to B is equal to H is equal to A. So if we are talking about TSA, it is going to be 6A square. If we are talking about LSA, it is going to be 4A square. And if we are talking about volume, it is going to be A cube. Okay, as simple as that. Now, yeah, let's do one question. If edge of a cube is increased by 20%, find percent change in its part A, TSA, and part B, volume. You like to try this question?
Yeah.
Okay, go ahead. Like even if you are not getting an integer answer, you can just tell the fraction answer, whatever you are getting. Okay.
Okay. So for TSA, is it 176?
Uh, I guess you have to change. You have to calculate the percent change.
Yeah,
Okay.
176%.
Okay. I don't think that is the answer, but yeah, we'll see. What about the volume?
Oh, it's actually is a 44.
Yeah, TSA is
Okay.
44.
Okay. And the volume is give me a second. So wait. 72.8.
Mm. Yeah, if this thing is what you have got and you have changed it to fraction, then it's okay. Yeah, you will get 72 point
Yeah,
something only, 70 something only.
72.8. Yeah.
Yeah. Okay. Now, do you know the difference between this term volume and capacity?
No.
Just a second. Okay. So, there is like these two terms are basically used interchangeably. But say, for example, we have a container, something like this. Okay. So we have a container, something like this. Now, when we'll be talking about the volume of this container, like we are seeing it from the outside, right?
Mhm.
So when anyone has not told us that this container is actually hollow from inside, this space is empty, right? The inner surface is empty. So when anyone has not told us that the surface is empty from inside, then what we'll call the volume of this whole figure to be this much. Okay. Actually, the volume of a substance is equal to the capacity of the container, like the amount of any substance that it can hold, right? But that is actually the definition of capacity. And we basically we tell that volume is actually equal to capacity, right? But that is not always the case. What is the volume of the container? Then we'll say that this whole thing is the volume of the container, because volume is whatever whatever volume, whatever space the object is occupying. Say for example, this is a 3D figure, this is a hollow sphere, say for example. So if this is a hollow sphere, even if the inside of the surface is empty, but still it is covering this much of volume, right? Can we put something in this empty space? No, because this is a closed figure. So for example, a tennis ball. Can you put something inside of a tennis ball?
No.
Okay, because it is empty from inside. So when we'll be asked the volume of that container, when even when we are asked the volume of a football, what do we call the volume of a football? A football is something like this, right? And the
Mhm.
inside of it, air is filled. So when we are asked the volume, let's say this is R, this is small r. What do we call the volume of the sphere to be? We call it to be 4 by 3 pi r cube, right?
Fire. Yeah.
We don't say
You have
that
to
it is equal to
subtract
4 by
both.
3 pi r cube minus r cube. This we don't say as the volume of the uh, football, right?
Is that the capacity?
Yeah, that is what we are coming up onto next. But yeah, we are understanding what is volume. The amount of
Yeah.
space that the object is occupying is simply what we call as volume. But when we are talking about capacity, capacity is all the space which can be filled by anything. Say here, let's say this is empty and this is solid. Okay, this is solid. This is a solid thing, and only the inside is empty. So if we want to fill inside of this container, what volume would be able to fill? This volume only, right? Because this volume is already occupied. Now, if this is, sorry, if say for example, the- yeah. So now, let's say for example that this empty space is empty, but mm, yeah, this space right here is the only space in which a hole, like a hole is there through which we can pour water. Okay, but the hole is not present on the surface of this sphere, this inside sphere. Then the capacity of the container would be what? This much only, right?
Mm-hmm.
So capacity totally
Oh.
depends upon the volume that can be filled with anything. The amount of any substance that the figure can hold. So that totally depends upon the figure's geometry. But volume is all the space that it is occupying. It is because in the questions that we are being told that this is a hollow sphere and you have to find out the volume. That is why, see, we know that it is a hollow sphere. It is hollow from inside. So the total volume it is occupying, the total space it is occupying, we take that space, we assume that space to be for the solid part only. That is why for a hollow sphere, because it is mentioned in the book, in the question, that is why we take only this volume for the hollow sphere. But otherwise, if you see the football example, if nothing is given and in a generic sense the volume of football is being asked, then we don't call it 4 by 3 pi r cube minus r cube. We call it 4 by 3 pi r cube only. Right.
Mm-hmm.
So it's a game of perspectives again. But yeah, I think I have made you understand about the difference between these two figures. Am I right?
Mm-hmm.
Okay. Okay, let's move on to the next discussion, which is right prism.
Okay.
So this is a very interesting concept. So for any figure to be a right prism, there are three conditions which it should satisfy. First one being two identical and parallel bases. Okay. The second one being rectangular sides connecting the bases. All angles between sides and bases are 90 degrees, are right angles. Okay. Now let's draw a cuboid, sorry, and discuss the same thing for a cuboid. Okay. Now, what is the first condition for a figure to be a right prism? That there should be two identical and parallel bases. So these two are exactly identical or congruent, and these two are parallel as well. Am I right?
Mm-hmm.
First condition is being satisfied. Now, rectangular sides should be connecting the bases. So these two are the bases which are being connected by what? First rectangular side,
Rectangles.
second rectangular side, third, and the last one, fourth one. Right? You can say that these two go like side by side. If the rectangular sides are connecting the bases, then all angles between side and bases are right angles. Like this is the side that is connecting, and these two are the bases. The angle is right angle. Okay, this is the side, these two are the bases, this is right angle. Also, this is right angle. So obviously it is right angle. So these 2 points go side by side. So these two are also satisfied. Okay, just a second, let me give you another example that I have to copy another figure. Hmm, where it is, yeah. The screen is visible, right?
Mhm.
For the other example, so this is our figure. I'll be drawing it, it will take so much of time. Okay, so again, let's see for the three conditions if they are being satisfied or not by this one. So there should be first of all two identical and parallel bases. So this is a hexagon over here, okay? And again the same hexagon here as well, okay?
Mhm.
So definitely they are parallel as well as identical, congruent to each other, okay? These two hexagons are identical and parallel, which are the bases for this figure. Now they should be connected by rectangular sides, or they should be connected by rectangles. So these two, which were the congruent faces, congruent edges for the hexagon, these two are connected with the help of a rectangle like this. Okay. Similarly, the same thing goes for these two faces as well, these two as well, these two faces as well, these two faces as well, and these two faces as well. Are you able to see what I have drawn?
Yeah.
Okay, very well. Now the angles between the side that is joining the bases and the bases should be 90 degree. So this is 90, this is
Okay.
also 90. We have drawn it in 3D, that is why this is not like uh, we cannot exactly see it to be 90, but this is not like this is not bent like this is a 3D figure. So this is on the same plane and this angle is equal to 90 degree, and the same thing goes for this angle as well. Okay,
Mhm.
similarly these two angles are also 90 90. This is also 90, this is also 90, because this is a rectangle, this is also a rectangle, so everything has to be 90, right? So it means all three conditions has been satisfied for this figure as well. It means this is also a right prism. Okay.
Yeah.
So this is what we call as hexagonal. Actually, the name for this figure is hexagonal prism only. But yeah, this is a right prism. Okay, this is a right prism. So hexagonal right prism or directly hexagonal prism, you can say. Okay. Any doubts?
No.
Now there is another topic called pyramids. Okay. So just a second. Yeah, I'll draw two pyramids for you. The first one will be with a rectangular base. This is obviously with a triangular base, not rectangular. Yeah, zoom this in. This is a triangular pyramid. Okay, now I'm going to draw a square pyramid for you. Okay, or we can also say a rectangular pyramid. And why I'm going to draw that? Because we have to calculate the volume out in that figure. Okay,
Okay.
that is why that shape is necessary. So you have to assume that this is a square. You are not assuming it from where we are assuming, like you are not seeing the figure from where we are seeing it. Okay, this is not 2D like this. This is 3D. You are actually seeing it from somewhere here. Like you are seeing the figure from somewhere here, right? Your eyes are somewhere here. Similarly, in this case also your eyes are somewhere here, and this is again a square. You'll be able to see it when I draw the complete figure. Okay, just
Yeah, I can see it.
okay, very well. Okay, this is height h. Okay, okay, okay. So now are you able to see that the base is a square?
Mm-hmm.
Okay, very well. This is a square pyramid. Okay, it means pyramid is basically just a shape in which uh, like the base is being joined by lines which are meeting almost above the center of the base. Right, this point, this vertex of this pyramid is above the center. This vertex is above the center of the base. Okay, now the volume for this one. Let's say, for example, this was A and this was also A. Okay, the square's edge length. Now, the volume would be equal to 1 by 3 A square h. Now you will ask that from where this has come. So let me tell you the formula for it. Uh, volume is basically equal to 1/3 of the volume of right prism from which it has been cut down. Okay, let's understand the statement now. So the volume of a square pyramid, like it is valid only for this square pyramid. I'm not telling that if you have to find the volume of this triangular pyramid, you will find out the area of this thing, and uh, like what we have done here, we have found out the area of the base, multiplied it with the height, and we have multiplied 1 by 3 to it. But the same thing you cannot do here. Okay, I'm talking just about a pyramid whose base is actually a what?
Where?
Yeah, base is actually a square, or it could also have been a rectangle as well. Okay, so the
Where?
volume is equal to 1/3 of that volume from which this right prism has been cut down. Say for example that there there is a right prism. What is a right prism for a rectangle, for a square base? It is a cube, right?
Mm-hmm.
It is a cube, and from this cube, this part has been cut down. Okay, this part has been cut down, which we have drawn here. So that volume is going to be this volume right here. This volume is occupying 1/3 of the volume of the whole figure. You are getting it, right? This blue volume that I have drawn, the bigger version of which we have drawn here, this is occupying 1/3 of the total volume of the cube. But it is
Okay.
not actually a cube here. If it will be a cube, this height will be equal to A. But here we have taken it to be h, so the volume would be A square into h. Because what is volume? Volume is the base area, it multiplied by the integration over which we are, like the height over which we are integrating this area to be. Okay. In that case, it
Okay.
will be a square h, and what we have done, one third of the volume. As simple as that. Again, if it were not a square but a rectangle, something to be like L and B, or L and B like this, then it would be 1 by 3 LBH. Okay. All right.
Mm-hmm.
You have written down anything? Any doubts? All right.
Yeah.
Okay. Like the lecture for this content is finished, but let me see that if I have the difference between the two figures.